What is up, guys? The power of pi here. And today we're going to be looking at a nice application of integral calculus, and that's in determining the moment of inertia of certain geometric shapes. So first, let's review what moment of inertia is. Now, in a discrete sense, moment of inertia is kind of like a way to determine the inertia for a set of particles. For example, if I have a coordinate system where I have point particles, as such, the moment of inertia is determined by taking a sum over the n particles and by taking the mass of the individual particles and multiplying it by the distance respectively from the axis of rotation. So in a discrete sense where you can count the number of particles, this is how we determine the moment of inertia. And moment of inertia is important, for example, when calculating angular momentum. So if angular momentum is conserved, for example, an object with more moment of inertia, which we can kind of think of as having more mass farther away from the axis of rotation, will have less angular rotation for if angular momentum is conserved. So moment of inertia has many applications. What we're going to concern ourselves with is when we're not actually dealing with moment of inertia in this discrete sense, but rather in a continuous sense, where really we don't have particles, but these particles are actually combined to form some geometric shape. In that sense, a summation doesn't do any good anymore. In fact, we're going to be taking infinite number of summations. So that's a very good idea that we're going to actually have to integrate. So let's see how that works with the next couple of examples. So first, let's look at kind of a rod, kind of like a one-dimensional rod that's rotating about this axis of rotation. And let's say that the length is L. So this is L. I want to determine this moment of inertia. Now we said that for a countable number of particles, this was the formula. So naturally, if I'm having a continuous set of particles, I actually want to integrate. So I want to look at a tiny slice of mass dm, and I simply want to integrate across dm times the distance from the axis of rotation, which we can call r squared. So if I can find this, I find the moment of inertia of the continuous shape. So let's apply this definition. So over here, the moment of inertia of this rod will be, I'll use the variable x instead of r, x squared dm. Now, what is dm? We need to figure out what dm is in terms of x so that we can actually integrate this, because right now we don't know what dm is. So dm is, how are we going to relate this to dx? Well, what I'm going to say is that this rod has line density of lambda. And line density is basically the mass over length per unit. So dm would then be this lambda, which is the density at some point, times dx. And this works out because if we were to check the units, lambda will have units of mass, or I should say kg per meter, and then dx will have length of meter. So this works out in units. So we have that this relationship is true. And we can plug this in to our integral to get this is the same thing as the integral of x squared lambda dx. And since now we know what x is, we can actually put in appropriate bounds. This is from 0 to L. And now this is an easy integral to evaluate. We have lambda integral 0 to L of x squared dx. This is lambda again. Since this is a uniform rod, the density is going to be uniform throughout the entire rod. So the density will just be the mass, which we'll call m, over the length, which is L. And then when integrating x squared, we get x cubed over 3, evaluated from 0 to L. And then this is m L squared over 3. So that's our first example. Now let's move on to when we have our same rod. It's rotating on an axis through its center of mass. So now we want to find the moment of inertia. Well, now actually the mass roughly is like it's a less distance from the axis of rotation. So we suspect that the moment of inertia is going to be less than what we saw. So we expect that the fraction is less than 1/3. So let's actually verify this. We again have an integral of x squared dm. And again, we have a differential piece dm is going to be equal to the line density, lambda, times that differential, this differential width, you can say. So dx. So this is going to be, again, integral. I can pull lambda out since it's uniform. We're going to be dealing with uniform shapes throughout this video. So we can pull the lambda out and we get x squared dx. Now, what are our bounds of integration? We're going to actually integrate from this point here to this point here. So this is actually negative L over 2, and this is L over 2, since the rod has length L. So I'm going to do something that simplifies calculations a little bit. I know that this is an even function. So I know if my upper bound and lower bound are actually the same. I know that integrating this is the same thing as taking twice this and starting to integrate from 0, as shown in the diagram here. And then this is now easy to do. 2, again, this is m over L, and this is x cubed over 3, evaluated from 0 to L over 2. So this is 2m over L times L cubed over 24. So this is 112 ml squared. And as we saw, we actually do have a lesser moment of inertia, so we have a good idea that our answer is correct. So now with rods out of the way, let's move on to circles, I should say. Let's consider a hoop. Now, a hoop is kind of an object where all the mass is distributed a distance r from, or I should say a distance x from the axis of rotation. So how can we deal with something like this? Well, again, we're going to invoke our definition that the moment of inertia is x squared dm. Now, x squared is constant throughout this whole problem. So we can actually simplify this by just taking x squared out, and we're going to just integrate dm. But that's an easy integral. If we integrate dm, we're just going to get the entire mass. So actually, the moment of inertia of a hoop is simply just mx squared. So with this, let's actually move on to a disk now, which will prove important. For a disk, it's something like this, where we have the origin here and then an axis of rotation, and we want to find, and basically there's mass throughout this like entire thing. And we want to be able to find the moment of inertia of this. So now we're going to take a more standard integration approach. What we're going to do is we're going to integrate by using small annuluses, which is basically kind of this region over here. So how can we do that? Well, we're going to just use our definition, in a moment of inertia is x squared dm. Now, what's our differential element of mass going to be? This time I'm not dealing with a line anymore. I'm dealing with area. So we're going to define sigma to be the surface area density and we can use that in the problem. So dm will be equal to sigma times a differential element of area, so dA. Now what's dA gonna be? So as we said, our plan for this is to actually take small rings, integrate small rings in order to get the moment of inertia. So dA is actually going to be equal to pi times kind of our integration variable x, pi x squared, and then dx. This piece over here, dx. So now piecing this together, we get I is equal to the integral of sigma pi x to the fourth dx. Is that right? Yep, seems right to me. And this is gonna now, since we're integrating with respect to x, we can use our bounds now. I'm gonna start from 0, and I will end at some radius r, where r is basically the radius of the disk. So the integral we want to calculate is from 0 to r. Pi is constant, sigma is constant, since again we're working with a uniform disk. And then this is from x to the fourth dx. So sigma is nothing but what? The mass over the area. The area is pi r squared. And then now we are going to integrate x to the fourth, which is basically x to the fifth over 5 from 0 to r. And then this is equal to, okay, looks like I made a mistake because I know I should actually get an r squared in my answer. So let's see where I went wrong. Yeah, okay. So the place I went wrong was actually in my dA. Let's carefully think about what it means to take an area of a ring. We're actually going to be taking 2 pi x, which is basically the circumference here, and then multiply by dx to get the area of a small differential ring. So actually, I need to modify this to now be x squared dm, and then dm is, okay, so this is going to be 2 pi sigma x cubed dx. And then this should be right. Okay, so let's just modify. 2 pi sigma integral 0 to r of, this should be x cubed dx. This is 2 pi times the mass over pi r squared times x to the fourth over 4, evaluated from 0 to r would be r to the fourth over 4. So this cancels. So we're left with mr squared over 2, and that checks out. So reiterating, we invoke the definition of moment of inertia. We find dm by actually considering integrating through some small rings. And the area of those rings will be 2 pi x, which gives the circumference at that x, multiplied by a small dx. And then with that, we can find dm, and then we can integrate in the x world from 0 to r. So with that out of the way, now let's move on to kind of the final, most complicated example we'll be doing in this part. There will be future parts in future videos. So we're going to actually now look at a sphere. And I'll present 2 ways to actually find the moment of inertia of a sphere. So I'm not very good at drawing spheres, so we're going to have to use a cross section for now. So imagine that this is a sphere. So we want to find the moment of inertia of a sphere. How I'm going to do this is I'm actually going to take cylindrical shells. So the moment of inertia is x squared dm, and I'm going to be taking cylindrical shells. So I can actually take small cylindrical shells that look something like this. And basically what I can do is I can go from this point, which is 0, to this point over here, R, by taking these cylindrical shells. So let's first look at what dm is. Dm is going to be, it's not going to be lambda, or it's not going to be sigma. Since we're dealing with 3 dimensions, we're actually going to have to use regular density, the first density we're typically introduced to, which is volume density. So dm is going to be some rho times some differential element in volume. Now, how did we say we're going to find this volume? We said we're going to find this volume by finding kind of the volume of this cylindrical shell. And how do we do that? Well, we take the 2 pi and we take whatever our integration variable is x, and then we take dx. Well, what's the height going to be now? The height is the challenging part. Let's go to this is kind of misleading because we're going to look at the origin now, and we're going to think how we can find the height. Well, let's clearly look at a slice over here, kind of part of our cylindrical shell. We're going to be a distance x here, and from the top here, there's a distance r. So we can use the Pythagorean theorem to find that half of the height is root r squared minus x squared. So the full height will then be 2 root r squared minus x squared. Okay, great. So now all we have to do is we have to integrate this. Now, what are our bounds going to be? We're going to start from 0, and basically we go until r. And at every step of the way, we basically take kind of this x over here, and then we just we pretend to like rotate it around and then create a cylindrical shell. And in that way, we basically get the volume, or I should say the mass, or I should say the inertia of the entire sphere. So we're going to integrate from 0 to r of this, and we have a lot of constants we can pull out. We can pull out 2 pi rho, and then all we'll have left is x root r squared minus x squared dx. Now the goal is now to figure out how, and I'm actually missing something. This is just dm, we have to multiply by x squared, so this will actually be x cubed. So the moment of inertia is this. So let's move this to another page. So the sine integral can actually be tackled using a simple u substitution. Let's let r squared minus x squared be u, and simply differentiating both sides, we get negative 2x dx as du. So x dx is du by negative 2. That's all and well, but we typically we really want an x cubed dx. So how can we find that? We know that x squared, by rearranging this, is r squared minus u. So that provides a great way. So x cubed dx will be actually r squared minus u du by negative 2. Great. So now all we actually need to do is find integral, which is 2 pi rho. Then I think I'm missing something actually. Yeah, there's a 2 here, there's a 2 here. So it should actually be 4 out in the front. Now the integral is, let's change our bounds. We see that r squared minus x squared is u. So on the bottom, we're going to have r squared. And at the top, we're going to have r squared minus r squared, so 0. And then now let's convert everything to u's. We'll have, okay, how are we going to do this? Negative 1/2 r squared minus u. And then root r squared minus x squared will be root u du. So this is going to be, I will use the negative to flip over this, and then I'll distribute the 2 out in the front. to make this 0 r squared of r squared minus u. I'll write a little bit more clearly. R squared minus root u du. And then finally, we can perform the integration. This is going to be 2 pi rho. And then this is going to be r squared root u du. So root u is going to be u to the 3/2 over 3/2. So this is going to be 2/3 r squared u to the 3/2. And then u root u will be 3/2. So that'll be u to the 5/2 over 5/2. So basically, this is going to be negative 2/5 u to the 5/2. And what we're doing is we're going to evaluate this from 0 to r squared. And that's good news because the 0 will now cancel, since 0 to the power of anything is really just 0, except 0, but that's not of relevance right now. So we can substitute most of this. 2 pi, what is rho? Again, it's a sphere of uniform density. So rho is going to be nothing but the mass over volume. So this is volume is 4/3 pi r cubed. Again, that's another calculus exercise to derive why that's true. So we can actually put the 3 here, and then 4 will stay here. Okay, and then finally, we're going to plug in r squared into this. We will get 2/3 r to the 5th. And we will get minus 2/5 r to the 5th. And then hopefully, we're almost there. So this is going to be cancel to big at 2. 3m over 2r cubed times, this is going to be 10. So this is going to be like 4 over 15. Okay, so what is this going to be? This is going to be 2, this is going to be 5, and this is 2/5 m, and this cancels to be r squared. 2/5 m r squared. And that is indeed the correct expression for the moment of inertia of a sphere. Let's look at one more way to do it. This time we're going to take our sphere. And rather than, use cylindrical shells, we're going to actually use discs again. We're going to use discs like this. Or, yeah, we're gonna do it like this. We're actually going to, it's not technically a disc, since we're actually going to be taking a very, very, very small height. But that height's going to be so negligible that the same process works by using the moment of inertia of a disc is mr squared over 2. It's similar to how we find the volume of a cylinder by doing pi r squared times height, even though we're stacking flat circles. So first, let's think about how we can find the moment of inertia of the sphere. Well, this is just going to be the integral of basically all the moment of inertia of the disks. So if we integrate over all the moment of inertias of the disks. Now, what's the moment of inertia of a disk of mass? Say this mass is of dm. This is going to be, the moment of inertia is going to be dm. Again, we're going to call the radius x dm x squared over 2. So really what we want to do is we want to integrate x squared over 2 dm. And then we'll specify the bounds once we find dm in terms of x. So what is dm though? Dm is going to be some volume density, rho, dv. And what is dv? dv is going to be nothing but pi x squared. Now we actually need a height variable. We're going to call this dy. Okay, so we have some information here. So let's see what we can do. Okay, this is other stuff. We can actually we can factor out a rho pi over 2. And then we can take the integral of x to the 4th with respect to dy. Well, this integral doesn't really make any sense, right? We're actually taking x to the 4th with respect to another height variable. So how can we rectify this? Well, let's see. So Okay, like this. So this is going to be the origin. Let's see if we can employ a similar kind of Pythagorean theorem thing. This is going to be the height y. This is going to be x, and this is going to be r. So basically, by Pythagorean theorem, x squared plus y squared is r squared. So we can actually relate x to y. And so basically what that's saying is we can relate the radius of a disk to basically the distance from the center of the sphere to the disk. By this Pythagorean relationship, x squared is r squared minus y squared. So we can actually solve this by taking this, by performing this. And now we just need to find out what our limits are. Well, y is going to range from negative r to r. That's pretty simple. And then this is in fact an even function. So we can rewrite this as rho pi, basically taking out a 2 and then putting this as 0 to r of r squared minus y squared squared dy. Great. So now let's do the integration. I'm going to directly substitute what rho was. Rho was mass over the volume, which is 4/3 pi r cubed. So this was again 3m over 4 pi r cubed. Let me just make sure. Yeah, don't want to make a mistake now. And then what we're going to do is we're multiplying by pi, and then we are taking this integral. So we're going to have an r to the fourth. Tacked onto that will be a y. We'll have a negative 2r squared y squared. That'll be negative 2r squared y cubed over 3. And then we'll have a y to the fourth, which will be a y to the fifth over 5. And then this is going to be from 0 to r. Okay, so this is going to be 3m over 4r cubed, right? And then this is going to be r to the fifth minus 2/3 r to the fifth plus r to the 5 over 5. Let's see, what is this? This is 3m over 4r cubed times, if we do the arithmetic, we get 1/3 plus 1/5, which is 8/15, I think. Yep, 8/15 r to the fifth. And right now we see we're almost done. This is 2, this is 5, this is r squared. So we get 2/5 mr squared, which is exactly what we found by doing a cylindrical shell method, as shown by this diagram. So hopefully you enjoyed this nice and comprehensive video on moments of inertia, where we looked at how to find the moment of it, what the moment of inertia is, why it's helpful in like angular conservation of angular momentum type situations, and then how to find the moments of inertia of certain like rods, a hoop, a sphere, and a disk. Next video, I'll be doing more examples on cylinders and kind of like other flat surfaces, and stay tuned for that. Thanks for watching.